There we are. Have a good session. You're ready to go.
Thank you, Kay. So welcome to the final session of AsiaCrypt 2020. The session is about attribute-based encryption. We have 5 talks, and as usual, each talk will be given in 5 minutes, followed by the time for question, maybe 5 minutes after each talk. So during the talks, if you have any question or comment, please post it in the Zoom chat or post it in the Zurich chat system. So let's begin. The title of the first talk, first presentation is Adaptively Secure in Product Encryption. And the authors are Shuichi Katsumata, Ryo Nishimaki, Shota Yamada, and Takashi Yamakawa. And the speaker is Shota. Please start. Shota, please unmute.
So do you hear me?
Yes.
Okay, so thank you for the introduction. So let me start the presentation. And so let me begin with the definition of attributes-based encryption, which is a generalization of ordinary public key encryption and inner product encryption. So in ABE, there are master public key and master secret key. Using the master public key, you can encrypt a message for some attribute X. And using the master secret key, you can generate a secret key for some attribute Y. And the decryption is possible if X and Y satisfy some relation. And in inner product encryption, or IPE in short, X and Y are vectors, and the decryption is possible if X and Y are orthogonal. In fuzzy IPE, X and Y are sets of some attributes over some universe, and the decryption is possible if the intersection of X and Y is sufficiently large. So let me explain some background on lattice-based ABE schemes. There are 2 major security notions for ABE, selective security and adaptive security. In selective security, the adversary chooses its, the selective security is defined by security game, and in selective security game, the adversary has to choose its target at the beginning of the game, even before seeing any parameters. On the other hand, in adaptive security, the adversary can choose its target adaptively, as the name suggests. And in selective setting, we have many constructions. In particular, we have ABE scheme for all circuits from lattices. However, if we require adaptive security, not much schemes are known. Ever since the first adaptively secure ABE scheme is proposed, there has not been much progress in this area. And recently, the elegant work by Sabari constructed the first adaptively secure ABE scheme for TCNF formula for constant T from lattices. But there is still a huge gap between the expressiveness of adaptively secure construction and selectively secure construction. So to fill this gap, we propose to ABE scheme for inner product predicate and fuzzy IBE predicate. And the caveat here is that our IBE scheme can handle inner product of a small integer or polynomially bounded integers, or modulus with small ZP with small modulus P. So let me explain our approach very briefly. We followed Sabari's framework for constructing adaptively secure ABE. In her framework, she combines adaptively secure single key CPRF with some property that is called conforming property and lattice evaluation algorithm. And in Sabari's work, she uses CPRF scheme for TCNF formula to obtain the ABE, adaptively secure ABE for the same predicate. A natural idea to generalize her framework or to have a construction with a more expressive predicate is to replace the CPRF part. In particular, we want to use the CPRF scheme for inner product predicate recently proposed. However, this construction does not have conforming property, and this framework does not work immediately without any change. So let me explain what is conforming property and why it is required. In Savarez's framework, she requires two matrices that are obtained by two different parts of homomorphic computation to be the same in order for the correctness to hold. These two homomorphic computations are defined by the underlying CPRF scheme. And the point here is that these homomorphic computations are equivalent as functions, but they are not necessarily equal as circuits. And this implies that these two matrices are not necessarily the same. And so in order to overcome this problem, she restricts the class of the CPRF scheme. She defines conforming property for the CPRF scheme. This property directly requires that these two computations are equivalent as these two computations are equivalent as circuits. However, this is a very strong property. If the construction has this property, then the framework works. However, this property is very strong, and in particular, the CPRF scheme that we are going to use does not have this property. So we have to overcome this problem. So let me explain our technique in very briefly. Our key observation is that the computation in the previous diagram can be divided into two parts. The first part is linear computation over the integer, and the other part is nonlinear computation over binary strings. And our another key observation is that if the computation is linear and over the integer, then the two matrices obtained by the computation are the same if the homomorphic computations applied to the first matrix are functionally equivalent, even if they are not equal as circuits. So we obtain the same matrices as desired. However, the homomorphic computation has not been finished yet. We have to continue the homomorphic computation. So, could
you speed up or wrap up?
We will finish soon. So, and this part of the computation is over the integer, and this part of the computation is over the binary strings. So we have to switch from integer to binary strings. So this part of the problem can be handled by using a homomorphic computation of Lagrange interpolation. So that's all. Thank you for the attention.
Thank you for the talk, Shota. So if you have any question, please post it in the chat. So in the Zoom, we don't. And in we don't. Okay, so maybe let me ask maybe quick question.
Yeah.
So does your technique also can your technique be used to obtain ABE for maybe richer class? Okay, how rich your class of ABE your technique can be used?
Maybe at most in a product, because our technique requires the computation of the underlying CPRF scheme to be exactly this structure, namely the linear computation over integer followed by general computation. So this still restricts the class of the CPRF scheme, and our scheme can only work for inner product or fuzzy IBE, which is implied by inner product encryption.
So for example, can the inner product be unbounded?
So
the
dimension of the inner product. I haven't considered this yet, but maybe not.
Maybe not all.
Yeah. And another limitation is that the size of the components in the vector should be polynomially bounded
Ah, yes.
rather than exponentially large.
Okay, thank you. So I don't see any other questions in the chat system. So maybe let's go to the next talk. Thank you, Shota.
Thank
Okay.
you.
Okay, I'm Fangguo Zhang from Sun Yat-sen University, China. Co-chair this session with Masuta. So next talk is unbounded dynamic predicate composition in ABE from standard assumption. The author is Natapon Archipondon, Junichi Tomida. Junichi Tomida will give us a talk. Welcome, Junichi Tomida.
Thank you for introduction. Can you hear me?
Okay. Yeah,
Okay, thank you.
you can start.
So AB is already explained by Shota, but all AB schemes are associated with predicate P, and each AB scheme consists of 4 algorithms: setup and key generation and encryption and decryption. And the decryption is possible only if the key attribute and Y and the ciphertext attribute X is satisfies the predicate P. And the predicate P is very important for AB schemes because it decides what kind of access control is possible in the AB schemes. And so there is one methodology to construct a AB to construct expressive AB schemes, and in which we can combine and enhancing existing AB schemes, less expressive AB schemes. And Attarpadung proposed a composition framework called dynamic compositions in Eurocrypt 19. And I will not go into details for dynamic compositions due to the time limitation. But this framework is very strong, and we can instantiate many AB schemes using the framework. And notably, we can instantiate AB schemes that simultaneously satisfying these 6 properties just by dynamic composition of IB and the negation of identity-based encryption. And constructing such AB scheme is very difficult, and no constructions are known before the Attarpadung's work. And the one drawback of his framework is it needs a parameterized assumption or Q-type assumptions. So the natural question is, can we remove the Q-type assumption? Because if we can do this, then we can obtain such a very important ABEs from standard assumptions. And the main contribution of this work is proposing a new framework similarly to Attarpadung's framework, such as dynamic predicate composition from standard assumptions. And we can instantiate many new ABEs from standard assumptions using our framework. And most notable one is unbounded ABE in the standard model. And the state of the art of unbounded ABE is that by Kowalczyk and we in Eurocrypt, it is presented in Eurocrypt 19, and it's simultaneously satisfying prime order groups and adaptive security and compactness and standard assumption. And we can instantiate a new unbounded ABE using our framework modularly, and we can obtain additionally, we can obtain ABEs which satisfies additionally large universe and non-monotone and CP ABE. Achieving adaptive security and compactness and standard assumptions simultaneously had been a a very difficult open problem, and which is solved by Qualcheck and we in this work. And we also we remark that we borrow this technique in our framework to achieve these ABEs. And we briefly explain the technical, high-level technical overview. And the most challenging point is how to achieve security of ABE. And the key property in Attar-Padung's framework was a symbolic property, which is introduced by Agrawal and Chase. And Attar-Padung showed that if ingredient ABEs have symbolic property, then the composed ABE also has symbolic property. And Agrawal and Chase showed that symbolic property implies adaptive security under the Q ratio assumption. So in his framework, we can show the adaptive security of composed ABE. But symbolic property essentially requires Q-type assumption. So we need another property to prove the security of ABE from the standard assumption. So we introduce an alternative notion called key encoding indistinguishability. And we show that if the ingredients ABEs have a key encoding indistinguishability, then composed ABE also has a key encoding indistinguishability under the MDDH assumption. And we also show that many non-ABEs also have the key encoding indistinguishability. Concretely, ABEs which can be captured by predicate encodings introduced by Hotek-Wee or perfectly master key hiding property of pair encoding schemes introduced by Attar-Padung. That's it. Thank you for your attention.
Okay, thank you very much for your talk. Any question or comments? So let me check the chat room. I didn't find any question in the chat room. Okay, here I have a question. So yeah, in your paper, you give a new framework of predict composition. But the assumption is, even you use the standard assumption is, I think it's just the traditional problem. So, you know, the lattice based crop system is a very hot topic recently. So I wonder if your work can move to the standard lattice based assumption.
I don't think so, because our framework relies on so-called dual system technique, which is often used for achieving adaptive security of ABE schemes. But we don't know similar framework in lattice-based ABEs, so we cannot apply this technique to lattice crypto, at least straightforwardly.
Okay, thank you. So, no, any other question? If no, I think, yeah, Matsuda-san, we can move to next talk.
Yes, thank you. So the third talk of this session is succinct and adaptively secure ABE for arithmetic branching programs from K-Lin. And authors are Fizher Lin and Ji Luo, and Ji will give a talk. Please start. Ji.
Okay, I just unmuted myself.
Yes.
Thanks for the introduction. This talk is about succinct and adaptively secure ABE for ABP based on K-linear assumption. I'm Ji, and this is joint work with Rachel. ABE has been defined in the previous talks. Let me quickly recap it. In key policy ABE, ciphertexts are generated for a message mu and tied to an attribute x. Keys are tied to a policy function f. if the policy authorizes the attribute, that is f of x is non-zero, then the key can decrypt the ciphertext and recover the message. This is equivalent to computing mu times f of x. And the security of ABE says that the message is hidden if the key is unauthorized. This should hold under collusion, that is, even when an adversary gets arbitrarily many unauthorized keys. The formal security notion is IND-CPA, which is standard in the literature. I want to emphasize that the challenge attribute is chosen adaptively after the adversary has queried many secret keys. And this is in contrast with the weaker selective security, in which the adversary must declare the challenge attribute before it sees the master public key. And of course, we want the stronger adaptive security. Aside from adaptive security, we focus on the efficiency of ABE, in particular, minimizing the ciphertext size. In most ABE schemes, ciphertext size is linear in the attribute length. It turns out that since the attribute is public and not hidden, the ciphertext size can be made independent of the attribute length. Such ABE schemes are said to be succinct. Note that this won't create a problem for correctness because the decryption algorithm will always get X, which is stored and transferred in the clear. In this work, we obtain concretely succinct ABE, supporting policies represented by arithmetic branching programs based on parent groups. When instantiated under SXDH, the ciphertext is just 4 source group elements plus 1 target group element, with the plaintext space being the target group. And our scheme is the first succinct ABE natively supporting arithmetic computation, whereas the other succinct ABE schemes are for Boolean computation. In addition, we also obtain ciphertext policy ABE with succinct keys. To construct our ABE scheme, our starting point is the framework of our previous work. It has 2 ingredients: a computational tool, function hiding, inner product functional encryption, and an information theoretic tool called arithmetic key garbling scheme, which is a special randomized encoding. Using these tools, we can construct compact ABE schemes, where the ciphertext grows linearly with the attribute length. However, it cannot be used as is to obtain succinct ABE. In a function hiding IPFE, keys and ciphertext cannot be succinct, which is inherited by the ABE. To overcome this issue, we replace the function hiding IPFE by a public key IPFE with a new security property proposed in this work, called gradual simulation security. Such a scheme could have succinct keys, which eventually translates to succinct ABE. I'll give you some intuitions on the construction in this work. I'm going to focus on a ciphertext policy variant. The idea is that when we put together a key and a ciphertext, we can compute a randomized encoding of mu fx and recover this value from it. The randomized encoding hides mu if f of x is 0, and it does not hide f for x. This is known as a partially hiding garbling. And thanks to being only partially hiding, the garbling can be very simple. In particular, the encoding is linear in X, and the evaluation is linear in the encoding. And we can compute it using IPFE. Actually, our ABE key simply is an IPFE key for the attribute, so our ABE inherits the succinctness from IPFE. The intuition for security involves 2 steps. First, by IPFE security, only the encoding is reviewed. Then by AKGS security, mu is hidden when f of x is 0. But these intuitions are very tricky to formalize, even more so than our previous work. Now, some technical highlights. We need 2 ingredients in the proof. First, we need piecewise security of AKGS from our previous work, which allows us to simulate the garbling in a clever way. Second, the proof must translate the simulation of garbling into a simulation of ABE keys and ciphertexts, which are a bunch of IPFE keys and ciphertexts. For this, the proof uses simulation security of IPFE in a quite unusual way, by alternating between simulating 1 versus 2 ciphertexts. This is not supported by the usual version of simulation security, so we need a strengthened version. And this is the gradual simulation security. It basically says that you can do or undo simulation for any ciphertext at any time, even in the presence of other simulated ciphertexts. We give a direct construction of gradually simulation secure IPFE by modifying an existing scheme. In addition, there's a generic transformation that converts any IPFE into a gradually simulation secure one. Due to the time constraint, I can't go into more details. Please make sure to check out our pre-recorded talk and our paper. I'll stop here and I'm happy to take questions.
Thank you, Z. So if you have questions, please put it in the chat or maybe you can unmute yourself and ask. So we have some conversation in the chat, but it is for the previous talk. In the chat system, I don't see the questions. So maybe let me ask a quick question.
Mm-hmm.
So you said that you have a generic transform for inner product encryption that upgrades to the gradual simulation security?
Yes.
So how, what is the efficiency of that transformation?
So the transformation will preserve key succinctness. So if the underlying scheme is key succinct, then the new scheme will also be key succinct.
Mm-hmm. How about the ciphertext size?
The ciphertext size will, it basically retains the original efficiency. Mm-hmm. So, but this, the efficiency will degrade as you require more simulated ciphertext, which is unavoidable. So aside from that, it should provide no degradation in efficiency.
Is there any other, you said that, one scheme directory. So do you have any other existing scheme that already satisfies your requirement, gradual simulation security?
Because I think previously no scheme considered simulating more than one ciphertext. Mm-hmm. So this notion doesn't make sense in previous schemes, but the previous scheme by Agrawal, Libert, and Stele can be modified for this version of security.
Thank you. I see. So we maybe don't have further questions. So maybe let's go to the next talk. Thank you, Z.
Okay. Next talk is in the production functional encryption with fine grained access control. The author is Michel Abdullah, Dario Catalano, Remy Gay, Bogdan Urso. Bogdan will give a talk. Welcome, Bogdan.
Thank you.
Ready?
Thanks for the introduction. Yes.
Okay.
Yeah. I hope you can hear me. So hi, everybody. Welcome to my talk. This is joint work with Michelle, Dario, and Roma. I will start first by recalling quickly the setting of inner product functional encryption. So here we have two parties, Alice and Bob. Alice wants to send the plain text to Bob, and this plain text is a vector of dimension d. Bob has a secret key for some vector y, and when it decrypts, it gets the inner product. And in terms of security, we want that the only leakage is the inner product and nothing else is learned about X. We know that from previous work that practical inner product functional encryption is realizable from standard assumptions. But in this work, the motivation is comes from the leakage of inner product functional encryption. And there is a lot of leakage that is derived from the ideal functionality. So for example, you can see that if you have the keys for canonical vectors, you can get the first component of X, second one, which is just from the definition of functional encryption. And maybe in practice, and this means that if you have linearly independent keys, then you can completely recover the plain text. And maybe in practice you don't want that, and you want to have more control over your leakage. So we look at a notion which combines attribute-based encryption with inner product functional encryption. So now the encryption algorithm takes as input an additional parameter, which is a policy P, and the keys have some attributes as well. When the policy is satisfied, you should get the inner product when it decrypts, and if they are not, you should not get anything. So our results are to instantiate this notion. We have several results. One is a scheme in pairing groups where the policies can be monotone span programs or orthogonality testing with attribute hiding. These schemes are adaptively secure. And the second result is identity-based inner product functional encryption with adaptive security in the random worker model and selective in the standard model. I will describe the high-level ideas for the pairing-based construction. Here we propose a framework that starts from the dual system attribute-based encryption and then adds the ALS scheme for inner product functional encryption. So how does this work? For this, I will have to recall at a very high level what predicate encodings are. These are just one-time secure private key statistical variant of attribute-based encryption. And it is known from previous work that one-time security, so predicate encodings which only have one-time security, their security can be boosted using dual system encryption to full-fledged ABE. This is known from previous work. And our strategy is to try to design a compiler that uses previous ideas, but also adds now adds inner product functional encryption to the compiler. So it's hard to explain the scheme. Maybe I can just give some ideas about how the proof should work, and then the scheme will be. You can try to guess what the scheme will be just based on the proof strategy. So proof strategy would be if you want to switch a challenge ciphertext that's for some challenge vector X star and some policy P star. And you do this in the presence of a master public key, which allows you to compute encryptions and some decryption keys, SKY for some attributes at. And if the policy is not satisfied, then you want to use the dual system security to switch your key to semi-functional. And if the policy is satisfied, then this is a step that doesn't appear in attribute-based encryption, because in attribute-based encryption, if the policy is satisfied, you can just get the message. There is nothing else to prove. But now, in this situation, we still need to show to have security from functional encryption point of view, and for that, the plan would be to use ALS security. And what you can notice here is that this kind of proof idea will only lead to a selective scheme, because you need to know these 2 bits in advance or the policy in advance. And we circumvent this limitation. And we also achieve adaptive security by introducing a new notion that generalizes predicate encodings called function encodings. And just to conclude, because there is not so much time, we have, as I said, pairing-based schemes for monotone span programs, orthogonality testing with attribute hiding, and identity-based encryption, and identity schemes, and multi-input schemes. And I can wrap up with an open problem. So we have also tried to obtain similar functionality from lattices. And the question would be, can we combine ABE for circuits with inner product functional encryption for lattices? So from LWE. For now, there are technical bottlenecks in how to do this. So we leave this as an interesting open problem. Thank you for your attention. And if you have questions, please not hesitate.
Okay. Thank you very much for your talk. Any questions or comments? So also I have a question. So I think maybe you know the constraint pseudo-random function, right? So constraint pseudo-random function we call the CPRF. This output a different string under some constraint inputs. My question is, if such a pseudo-random function can be used to replace the predict encoding or function encoding in your work?
The predicate encoding.
Yeah.
I don't know.
Use
really,
such a pseudo-random function to replace your predict encoding or function encoding? I don't just curious this one.
Yes, I will have to think about it. They are kind of different notions, right? I mean, with yes, I don't know. I will have to think. Thanks, thanks for the question.
Okay, but just discuss doesn't matter. So for the predict encoding or function encoding in your work, so is that very special, the coding method?
There are different notions, right? Like the PRF, the predicate encoding offers you statistical security, but only once, right? What kind of constraint PRF do you want to use? One that you can puncture multiple times? Do you still have statistical security for that? And I'm just trying to see if the notion would fit.
Okay. Thank you.
I don't know.
Okay.
Thanks for the question.
Okay. So other question or comment? So let me check the chat room. No other questions. So I think, yeah, maybe we can move to the last talk, and finally we just ask the other question. So yeah.
Okay.
I think, yeah, Matsuda-san, we move to the last talk.
Okay, thank you. So the final talk of this session is titled Monopoly, an expressive QSDH-based anonymous attribute-based credential system. The authors are C-Yuan Tang and Thomas Gross, and C-Yuan will give a talk. Please start.
Thank you, Matsuda. So I'm Tan, and this is the work by Thomas and I. We propose an expressive anonymous attribute-based credential system that we call Monopoly. So a quick recap on the concept of ABC system. In a credential system, there are two protocols. First is issuing protocol, and the second is the presentation protocol. In the issuing protocol, the user is allowed to anonymously obtain a credential from an authority, which is named issuer here. And then the user will act as a prover to anonymously convince a verifier on his identity. So in the attribute-based setting, if the credentials contains a set of attributes, then the verifier can also ask the prover to show that the attributes fulfill some access policy. So if the protocols end successfully, the verifier will accept the prover and reject otherwise. And they are efficient, highly efficient ABC systems in the literature, but they work under the finite set attribute space only. They can achieve such efficiency because they perform pre-computation on the limitedly many attributes. So they have either large public key size or large credential size. We do not find a comparably efficient ABC under the unrestricted attribute space. Besides, we also notice that there's a lack of systematic canonicalization of security models. So to close the gaps, we first propose a set commitment scheme that we call Monopoly. This commitment scheme can support set intersections and set difference operations. Using this commitment scheme, we construct a new ABC system which offers strong security assurance, practical public key size, as well as expressive but efficient show proofs. And this is how a set commitment looks like. So notice that in the public key, this is the instance of a Q co-SDH problem. And in order to commit to an attribute set A, the committer chooses a random opening value O, and it constructs the commitment as such. So this is the monic polynomial, which can be rewritten by using only the coefficients. And that's why we name this Monopoly. If a committer is going to show that the committed set A contains a set I, the committer can separate the set I out from the set A, and everything here can be compressed into a witness, and C and W can be verified using pairings. And same goes to the set difference. If the committer would like to show that there is no set D in the committed set A, the committer can show that there exists a quotient which can be compressed into a witness W, and that exists a non-zero remainder. So these two can be easily verified using pairings, and for the remainder, we simply check that it's not equals to 1. So using the set operation, we construct the access policy for the ABC systems. You can see that the true conditions are all about the set operations. And for the signing algorithm, we adopt the CL signature scheme, but we make changes on the verify algorithm. Instead of using the original verification algorithm here, we move the T to the right-hand side. And this is important for our randomization on the credentials. And our ABC system starts from here. The key generation is a combination of the monopoly set commitment setup and the CL signature setup. And the issuing works like this. The user initializes the issuing protocol by running a proof of knowledge on this element M. And if you have noticed, M is actually a Pedersen commitment on our monopoly commitment. So the issuer checks and signs on this using the CL signature. Later on, the user compile the signature into a credential. So before starting a presentation protocol, the user blind the credential as such, and this can be verified using the equation here. And this equation is actually the equation for the proof of possession. So in the proof of possession, you can notice that the front part is actually the open algorithm from the monopoly set commitment scheme. And this equation always works regardless of the size of attributes inside the credentials. That's why we have a constant size proof of possession. And for the end proof, the scenario is that the verifier asks the user to show that there exists a set A prime inside the credentials. So the user again make use of the monopoly set commitment scheme verification algorithm, and this value is the polynomial coefficients by the set A. It can be computed by the verifier. So again, we get a constant size proof. Then the rest of the show proofs work similarly. So you can see that the front parts are from the monopoly set commitment schemes, and the later parts are from the CL signature scheme. So if there is a composite proof of K clauses, we can actually stack all the pairings elements from the monopoly commitment. And for the later part, we only need to bring the equation to the power of K. So in this example, since there are only 2 clauses, so it's power of 2. And for our security, we prove that our proposed ABC system has impersonation resilience and unlinkability. And for our unlinkability, we propose a strong unlinkability notions. And we show that our unlinkability actually covers the anonymity notion. That's why we can achieve all the security properties here. And to the best of our knowledge, we are the only one that can offer type reduction. In terms of efficiency, this is a representation in terms of scalar multiplication in G1. So the lower, the better. Ours is at here. So the bold line. And those run faster than us are the ABC system that work under the finite attribute space only. We also implemented our ABC system using AMCL Java library. So for a credential of 500 attributes, we can complete our presentation protocols within 1 second at 128-bit security, and within 5 seconds for 256-bit security. So that's all for my presentation. This is the full version. So any question?
Okay, thank you.
Thank you.
So do you have any questions? I see no question in the chat.
So, hi Yuan, I have a question. So maybe this is just a very general question. So I find in your paper, actually in your scheme, there is a parameter n in your scheme. It seems that n is the size of an attribute set, right? The n.
Yes, n is the
Alpha
maximum.
1, alpha 0 to alpha n. Okay.
Yes.
So my question is, in general, how large is this parameter n? I mean the size.
It can be very large. For our simulation, we set it until 1,000 and it still works pretty fast. So if you increase this to, let's say, 5,000 or 10,000, I think it's still practical.
Okay, so this I mean this parameter n is not related to the security, just to the efficiency. Am I right?
Yes, correct.
Okay. Okay, thank you.
You're welcome.
Can I also ask a question?
Yes.
So your scheme is based on QSDH assumption. So
Yes, correct.
can we? Is there any possibility that we can make it without secure without QSDH, or maybe with some modifications?
Currently, I don't see this possibility, because if we don't use the QSDH assumption, then we will lose the advantage of type reduction. And from our analysis, we noticed that the security loss due to Chion's attack on QSDH assumption is not a problem anymore due to the recent advancement on the attack on pairings. So if we want to follow the new recommendation for the pairing security to secure in the GT group, that actually the increment of the parameters already covered the security loss by Chion's attack.
I see. So I also have other question, maybe simple one. So you propose a new set commitment scheme, I guess. Is it correct?
Yes, correct.
So do you have any other applications than this anonymous credential system?
Yes, of course, because we can, if you take a look on the this is actually very similar to the model of attribute-based signature or attribute-based identification scheme. And the issuing is actually the same as the key generation for attribute-based encryption. So maybe we can construct more attribute-based schemes by using the same set commitment scheme.
I see. Thank you.
Thank you.
So other questions in the chat? We don't have questions, I think. So if we don't have any questions, maybe we can finish the talk, and maybe we can also accept the questions for all speakers maybe in this session, if you have. Oh, by the way, thank you for the G1.
Okay, yeah, I think that's all of this session. Thank you for all the speakers and all the participants. And thank you, Kevin and Kay, for your hard work. Thank you.
Thank you.
Thank you.
I think we can move to, closing. Right? Okay.
Hello, everybody. This is the General Chair from the Kim. So almost the final work I have to do. Before closing the Asia Crypt, I'd like to introduce next Asia Crypt General Chair, Professor Jiyoung Guo. Okay, so can you give some information of next year?
Thank you. Let me share my slide. Okay, so I'll take 5 minutes to recap what we planned for Asia Cup 2021. So the plan is still there. So the dates will be the first week of December 2021 in Singapore for Asia Cup 2021. So the venue is Novotel Hotel. In this place, we've hosted several crypto conferences like FSC 2017, Asia CCS, DIAC 2015. The place is located just next to the Kui, and the facilities are quite modern so far. In Singapore, there are lots of places where you can visit. You can have fun at the beach, and we also have the newly built gardens by the bay where you can have a walk, and we have a vast variety of local foods you can enjoy. And also just within the walking distance from the hotel, there are many hotels with different prices, budget ones as well as the very decent ones, 5 stars. And all these plans are based on the assumption that we will have a vaccine soon and the situation will getting better by the end of December next year. But we don't really know. So the current plan is we'll be prepared for all 3 different options. So in-person conference or the virtual conference or the mixture. Nevertheless, I'm looking forward to seeing all in Singapore next year. Thank you.
Okay, thank you. So can you stop screen? I'd like to share my screen too. Professor Kuo.
Yeah.
Okay, so this is a final moment serving to the Asia Crypt. When we start Asia Crypt 2020, it was a friend to the physical. But unfortunately, we have to make it virtual. You see, this is my badge. I wear the Asia Crypt. This is 2019 last in Japan. This is 2018 and 2017, you know, that maybe in Australia and Hong Kong. I'm very sorry not to make this badge for you anyway. Maybe we can make it next year in Singapore. So I'd like to announce the final statistics. This is a dramatically increase of participant due to the virtual. So we have this morning up to the 789 and maybe 781 registration from all the 49 countries. It used to be more than 30 around in the normal Asia Crypt conference, but that's due to the virtual. A lot of countries are increased to attend. Also, that the regular person 485, student is 304. This is a good sign. Students are very interesting to start crypto. So also the Japanese #1 is 99, and United States is 94, and China is 75, and Korea is 74. 72 is France and Germany, and many other countries also attended Asia Crypt. Also, that is I like thanks special to all the members, including program co-chairs, Professor Wang and Moriai-san, they're on the screen, the Asia board of members, and the Kevin and Kay, all speakers, session chairs of the regular sessions and lump sessions, and 2 social hours, and participants from all over the world. I hope, strongly hope, we can see again in Singapore next year. 다시 만나요 in Korean, 맞다 아이마쇼 in Japanese, 再见 in Chinese. 감사합니다. Thank you very much. I like close the Asia Crypt 2020.